Hey, John here. So what's up with this 68k business? It turns out this particular chip has an impressive number of addressing modes, and therefore its documentation is very useful for the conversation on addressing modes and the different kinds. So let's take a quick look at how this thing is set up before we look at the doc, because you won't be able to understand it otherwise. So the 68K has 8 data registers and 8 address registers. Okay. The last address register, A7, is used as the stack pointer for this machine. Okay. Has a program counter, as all CPUs that I've ever heard of have as well. All right, now that's the main takeaway. There's 8 data, 8 address registers, and the reason you need to know this is because when we talk about the way the addressing modes work in a machine, you need to be able to specify which registers hold addresses and things like that. And only half of the registers that are in the 68K can be used as base registers, for example. That's the main takeaway of this diagram. Now we can look at this handout. I uploaded this to my faculty website. I'll put a link to it in the video below. If you look at the first paragraph here, this is clickable. It really just takes you to the last page of this PDF. You grab the scroll bar, go to the bottom of the page. There's a references thing here. Click this link right here, okay? The link will open up a PDF, which is the actual manual for the 68030 that was published around 1990. This is the manual you want to use for the diagrams. Somebody that doesn't know what they're doing got a hold of the manuals or became in charge of something, I don't know what, and they drew the diagrams in here that I want to use. They screwed them up at some point in the 1990s. So don't just go grab any copy of this manual. You want this exact one, all right? Or a hard copy, which you probably don't have, from the 80s, all right? Here's the section that we're going to be looking at, section 2.4, all right? This handout here is going to walk through a number of examples based on this section of the manual. All right. Okay, so here's the deal. I stole this right out of the manual. And addressing modes, what are they? Okay, an addressing mode of an instruction. You can use these things to specify the value of an operand, or it can specify a register number that would have an operand, or it can be an address that specifies where an operand might be stored in memory. Okay? So this is the main simplest definition I could come up with. Note the 68K family CPUs are big endian. All right, so in the examples that we look at in here, when we grab values out of memory, we're going to grab them in big endian order, which is nice because they're easier to read for illustration. And yes, they have 8 data registers and 8 address registers, as we saw on the Wikipedia page. Register A7 is normally used as a stack pointer when your program is running, for subroutine calls and things like that. This fact is important if you're going to program the 68K, but not really important in the examples that we're going to go over in this video. All right, so how do you use this handout? All right. The information on this page here at the bottom of page 1 represents a snapshot of the machine state in time. So each one of the examples that we discuss assume that this is the state of the machine before the example is applied, all right? So they're not cumulative. For example, if one of the examples set all the memory to 0, that's fine, but it only applies to the one example. The next example would start over again with a fresh view that this is the state of the CPU in the memory, okay? All right, so let's look at this thing. Let's see how to read this. Section 2.4 is what we want to look at, and I'm looking at page 53, it looks like, in this PDF. All right, so, and here's the paragraph I lifted for my handout. Shows you a little bit, talks some stuff in the context of the 68K. They define some terminology in here. Okay, effective address and address registers, the AN, the DN is a data register. You'll see there's scaled indexes and things like that, the current program counter. We have displacements, base displacements, outer displacements, and things like that, all right? Let's just knock these down one at a time. So this is going to be an enumerated list of the addressing modes and how they work, okay? Number 1, address register direct, which I skipped. I got data register direct. I guess I did mine in the opposite order. Sorry about that. Address register direct mode. What happens here is simply if an instruction specifies an address register in this mode, the value in the address register is the operand itself, okay? What did I write in here? The operand is in an address register if an instruction uses this mode and it specifies register A3, like, you're going to load some register with the contents of A3. That would be an address register direct mode. The operand value would be this, right? Because up in here, if we look at the value of A3, that's what it is, all right? So if I say, tell me what the value is of an address register direct value using A3, you can just go in there and say, there it is, right? I'm really asking you what's in address register A3, and you can extrapolate that data register direct is the same thing, and the operand is in a data register. And if I say D5, the operand value will be D5 33333, because up here that's what's stored in D5. Okay, now it gets interesting. And this is why we want this manual. Address register indirect mode. All right, no problem. So far, so good. The address register indirect mode, the operand is in memory, and it is stored in memory at the address that is in the address register down here, right? So if address register N, let's see what I got in here, has, if I use that mode, okay, and I say I use A2 to specify where I want to get my data, the operand will be this, because I'm fetching it from this address 50 in hex. Why? Because A2 has 50 in hex, and at 50 we got 3321837A, and that's what we grabbed out of memory, okay? That's no big deal. If you're familiar with mainframe assembly, let's get DXB address with a 0 displacement and a 0 index register, and in this case A2 for the base register, all right? Address register indirect with post-increment. What the heck is that? Well, let's get the picture. This is what we're in here for. Address register indirect post-increment mode. What happens here? This is the diagram that's screwed up, by the way, in all the other manuals. I think the other diagrams are fine, but this is one that is wrong. Okay, so what you have is the address register. You take the value, the contents of the address register, and it represents an address in memory. You see this arrow down here that says it's used to go get the operand out of memory, okay? Now, while it's going and getting the operand out of memory, it's also taking the memory address and it's adding a length value to it and storing it back into the address register. So that's this post increment. It is used to specify an address in memory of the operand, and then after that it is incremented and updated, right? So if you look at the narrative here, address register indirect with post increment mode, the operand is in memory and the address of the operand is in the address register. After the operand address is used, it is incremented by 1, 2, or 4, depending on the size of the operand, okay? So let's see what we got in my little handout over here. What's in my bag of tricks? FYI, this is a pop instruction when it's applied to a full descending stack. That's exactly what you need. All right? So this is a fancy way of saying it's a pop instruction with a full descending stack, okay? So what do we got? Operand is memory. After the operand is fetched, the address register is incremented to point to the next item in the stack below the one is popped out of the stack, right? So we increment it, keep it straight in head. You increment it to go to the item below the one you popped off because the stack is descending and we're popping, so that it has to go up in terms of addresses, right? So what do we got going on? For example, if I want to read a 32-bit value, and by that, I'm referring to the part of this diagram when it talks about the operand length, okay? If this is 32 bits, then the length is 4 bytes, right? I want to read a 32-bit value from memory and specify that A2 is the operand. Then the operand value will be this, right? Because I fetched from memory address 50, and then A2 will have been updated to 54, right? Because when you do a pop on a descending stack, after you go and get the value out of memory at the address in the register of interest, you increment that register by the size of the thing you popped. So that'll have to go up to 54. This thing here, if my handout is not screwed up, better be in memory at address 50, right? 50 is here, 3321837A, okay? And 50 is what is stored in address register A2, okay? Now, yes, A7 is normally used for the stack, or let me say a stack, a commonly used stack in the CPU. But because of this addressing mode, I can use any address register as a stack using this post-increment indexed mode, all right? So what do we got when we got address register indirect with pre-decrement? All right, let's look at the picture of that case. See how this one says use the memory address to go find the operand, and at the same time add 4 to it, and then store it back into the memory address. Look what happens with pre-decrement mode. Well, this one says, look, take the address out of an address register, but before I go out and grab the operand value, subtract the length of the operand. So I'm pre-decrementing, okay? And I'm storing it, update it back into the address register, and I'm using it as the address of the operand in question at the same time. And yes, of course, that's a push operation on a full descending stack, okay? So what do we got? It's in memory. The address register has to be decremented to make space at the top of the stack in order to push the new item into memory. So let's see what we got here. In the machine state above, if we want to write this value into memory, and I use A2 for my register, my stack pointer in this case, then the memory at address 4C will be overwritten with this value. Obviously, this needs to be stored somewhere if that's the goal, right? So it makes sense that you'd say, I'm going to store it somewhere, and A2 will be changed to 4C. So let's take a look at this thing here. What's going on here? 4C will be overwritten, and so what is the question is, what's the value of A2 before this thing runs? We've looked at it repeatedly. I believe it's 50, right? It better be. Okay, there it is. A2 is currently 50 before the instruction runs. Okay, at address 50, we've got all these values along in here. Okay, and at address 40 through 4F, we see these values up here, namely the 055689E9 here. This is what's going to get overwritten, okay? So we got pre-decrement. Okay, so A2, before the instruction runs, points at address 50 right here, the 33. It's going to be pre-decremented by 4, so that's 1, 2, 3, 4, okay? That's this 4C address it was decremented to, right? Then we're going to store the value in there, the 1, 1, 2, 2, 3, 3, 4, 4, and you can see that right here. So this is exactly what's supposed to happen with a push on a full descending stack, okay? So that's how to read this diagram. Let's look at some other ones here. They start getting interesting. Register indirect with displacement mode. Well, this is a base displaced addressing, right? Or a DB address, if you're familiar with that on a mainframe assembler kind of a thing. Address register indirect with displacement. Okay, so what we're really doing is we're taking the address register's contents and we're just adding a displacement to it. Now, unlike the mainframe, the 68K does a sign extension on this displacement. Therefore, what that really means is that this displacement can be negative as well as positive. All right. Now, because of the way this manual is written, this section is concerning itself with the actual encoding of these instructions. So what happens is, if they're going to talk about address register indirect with displacement, there might be two sections. So some of these are paired. This is a 16-bit displacement. And this other example is the exact same thing. Oopsie. Does this have an index? I'm sorry. Some of them are paired off. I'm jumping ahead. Strike that. Where are we? Address register indirect with displacement. Yeah, so you take the value in the address register, you add a displacement value, and that becomes an address within which you got the operand stored. So let's look in here, make sure I didn't screw this one up. Address register indirect with displacement. Okay, here's my push we just talked about. Now we're in section 2.6 over here. Okay, good. The operands in memory calculated as such. Okay, if we look at our current machine state, we use A2, which we know has a 50 in hex, and we use a displacement of C. Well, then we better go get our data or store it if it's a write operation. These examples are read operations, but the same thing happens if you're storing something. Okay, we end up with address 5C, and that would hold the operand in question. So hopefully in the dump up here at address 5C, there's 50, 5C starts here, DE63FCC4, and we see that's the value of the operand in question. All right, so nothing too terribly crazy just yet. Address register indirect with index. I'm sorry, yes, I misread when I was scrolling around over here. This is the full-on base displaced with an index, right? You know, the displace. We usually say DXB backwards when we're talking about these kinds of addresses on the mainframe. This is the one we're going to see two of. Okay, we see address with an index and an 8-bit displacement, which is exactly what you would expect. You've got your base address value, you got your index register value, and you have a displacement. The 68K happens to have an 8-bit version, and then right after this, we'll see the same exact thing, but you can even have a 32-bit version of the displacement value over here, all right? Unlike the mainframe, which is always fixed at only, 12 bits, I suppose. So this is a signed 32-bit displacement up to that in your base register, and you've got an index register. Now, this is kind of an interesting thing. The 68K also lets you multiply the index register by a scale before it is added to the base and the displacement value. All right, so let's look and see an example of that. Now, in my version of the how-to notes, these examples, I say from 8 to 32 bits, okay? I don't particularly care that whether it's a 32-bit displacement or a 8-bit, okay? For the sake of this conversation, it doesn't matter. So let's look at this diagram here, right? So we got the base index times scale, right? What do we got going on over here? So if I want to do a read of a 4-byte value, and I'm using register A2 for the base, which is address 50 in hex. I want to use register D1 for the index, and I can do that. It lets me do that on a 68K. And I use 4 for the scale, and I'm using 4 because I'm reading 4 bytes of the memory, okay? And then I'm going to use a displacement of 10 in hex. The memory address is calculated like this. Okay, let's take a look and see what's in D1 above here. D1 has the value 4 in hex. Okay, so where were we? There we are. That's this 4 right here. So A2 is 50 in hex. Base D1 is 4, and the scale is 4. So we're going to multiply that by 4, and we're going to get 10 in hex. Hex 1, 0. 4 to 4 is 16, and 16 is 10. So we got 50 plus 10 plus 10 equals 70. And in this example, again, I said let's assume we're going to read using this mode. Okay, we're going to go to address 70, and we're going to see that value, FDBC, and so on. 70, FDBC D6FA right there. Okay. Memory indirect post-indexed. Now this is where it gets really crazy. I've never seen addressing modes like this on other machines before. Look at what the heck is that. All right. Let's take a step back for a minute. What's happening here is we have an address register that's used as a base register here. And we're adding a displacement. So this is a displaced base thingy here, okay? That is done. It's added together. This is used to represent a memory address, and the CPU goes out into that memory address and reads a 32-bit value. And once it gets that value, it uses that as a base register along with an index register that is again scaled with another displacement. So from here down, this is base, index, displacement, like we've all been familiar with the addition of the scale, of course, okay? So what this does is it says your base register can the value of the base of your address can come from the memory itself. It's an indirect, right? So the address register plus what we'll call an inner displacement equals an address within which is your base value, base address, plus your index, time your scale, plus the outer displacement. And that address in memory holds the operand. So let's look at this example over here. What's going on with all this, right? Let's assume we're going to do a read, 4 bytes. And we're going to use A6 for the base, 10 for the base displacement, all right? That's referring to this displacement up here. This is called the outer displacement down there, okay? So we got A6 for the base, hex 10 for the base displacement, D1 for the index, 4 for the scale, outer displacement of 8. What does all that mean? All right, well, let's just do the first part here. A6 is the base and 10 and hex for the displacement. So what's an A6? A6 holds 8C, all right? Let's see if I got my example right. Okay, so we got A6, 8C plus the displacement, which is 10, gives us 9C. This address is the value here, which points into memory. You go into memory and you read from there to get the new base address, all right? So I say the indirect value here must be 10. So if we go up in our memory dump and look for what's in 9C, 90, 9C starts here. So it's 00010. Okay. So that is our new base address, all in one instruction here. Okay. So this looks good. Then the operand address is that 10 plus the index value. Remember, D1 has a 4 in it, and the scale is 4, so this is going to be 10. Add these together, and we'll get 20 in hex, plus the outer displacement, which is 8, and we end up with 28 in hex. That represents the operand address, right? So what's in 28 up here? 28 is right here, 1813CC01. 1813CC01, okay? All right, so that's memory indirect post-indexed. Let's go down here to memory indexed pre-indexed. Okay, so what is this thing gonna do? This is basically the same thing in the diagram here. Is a little more obvious to see what's going on as the post-index mode, except for what's going to happen is this index register here in post-index is just going to simply move from down here in the calculations to up on top, but it's otherwise going to be the exact same thing with this indirect memory address thingy in the middle. All right, so let's scroll down, have a look, see at this diagram. So you can see now our base address register, our displacement, the index register is now up here times the scale value, which represents an address that points to our other base register address, or I should say the other base address that's used with the outer displacement to calculate the final address that's used to represent the location where the operand is to be stored or read from. Okay, so let's look and see how that example works. I'm looking at the wrong thing here. Here we go, pre-index, here we go. So yeah, all we're really going to do here is we're going to add the scaled index first instead of later, right? So let's see what's going on here. In this case, what do I want to do? A6 I'm going to use for the base. I'm going to use this thingy here for the displacement. That's obviously a negative number. Then I'm going to use D2 for the index, 4 for the scale, and an 8 for the displacement, right? Those are the same registers we used up here, right? A6, D, oh, no, they're not, D1, so I use a different register this time. Okay, so let's look and see what the values are for A6 and D2. Double check, make sure everything's copacetic here. A6 is 8C, D2 has the value 1 in it, all right? So how do we use those guys? All right. D2 has 1 and 4 is the scale. So that explains this, right? There's the displacement. So we got the base address comes from A6, which has the 8C. We just checked that. Here's my displacement. Here's my index register value, which has a 1 in it, times the scale. 8C plus 7C is 8. Plus this, which is the plus 4, equals C. This is my indirect address. If we go look in the dump at address C, we'll find that there's an 80 stored in there, hopefully. So let's have a quick peek. Address 0, there's the address C right there. 80. Very good. So that's where that 80 comes from. We then use that as this operand over here, the value at the memory address, okay? Add on our outer displacement, okay? Our outer displacement is 8. So 80 plus 08 equals 88. And if you go look in the memory at address 88, there should be this value here. And this is an example of a read. If I did a write, it would do all the same stuff, and instead of reading, it would write something into that address. Okay. So at 88, we better see a DC16 something or other. 88, right? There's 80 DC1651A9. All right, so that looks good. All right, is that what we got? Yeah, okay, good. All right, now program counter indirect with displacement. Now we've seen this essentially in the RISC-V. And this is actually an incredibly common addressing mode, although it's not available on the mainframe assembler. The way this thing works is the same as any indirect with displacement kind of addressing mode, but it lets you use the value of the program counter rather than forcing you to use a value out of another register. Your base register can be the program counter, and that's how this works. Take the current value of the program counter. Emphasis on the current value. We'll come back to that in a second. Take the current value of the program counter and use that as your base address, okay? Add your displacement to that base address, and that's the address in memory where the operand will be, okay? So let's look at this example here. This paragraph is very important here. let's make sure we understand what that's all about. If you're going to look at the 68K stuff or read about other CPUs, you need to know that program counter relative addressing, which is what this is commonly called. Sometimes it's just called relative addressing, because that suggests that the program counter is the most likely register to be referring to if you don't specify in that kind of a statement. So what happens here is on the 68K, in most CPUs, the program counter register value that you use in the calculation is the value that it has at the time that the calculation is taking place in the CPU. That is not necessarily the address of the current instruction being executed. In a 68K, the program counter moves forward while it's reading chunks of the instruction. Now, to simplify things for the sake of this discussion, let's just assume that it is chunked forward by 2 bytes. So the value that you get out of the program counter when you apply it in this way, assume that it is going to be 2 more than the address of the current instruction that is being executed. All right? Now, this is different than what happens in the RISC-V. In fact, RISC-V is the only CPU I'm aware of that I recall off the top of my head that uses the address of the current instruction when it uses program counter style indirect with displacement calculations. Almost all other CPUs use some program counter plus something else plus the displacement when it's doing these calculations. So you need to look it up for your specific CPU. This is one of the reasons the RISC-V is a nice straightforward architecture to learn. Let's not get too caught up in this. I just want to make sure that you understand that some CPUs do this a little differently. For the sake of this discussion, let's just assume that when you look at the program counter, and if we look up at the top of this thingy, it says assume the machine state is these register values, including the program counter, equals 100 before we execute the instruction that we're talking about in each one of these examples, okay? So let's see here. What am I looking at? This one right here. Program counter indirect with displacement, okay? So this is why we're going to see a +2 in here. That's all I'm getting at, right? So read this very closely and understand this. So if the program counter is currently 100, in other words, and you use this mode in this example, we're going to just assume that the program counter has already moved ahead 2 bytes. So the program counter of 100 plus this extra 2, and that's what this manual refers to as the address of the extension word. This is part of a 68K instruction. And sometimes it's 2 bytes after the beginning. In fact, it could be quite often there. That's why I chose to use that value. So this is really 102, even though the program counter is 100 in it in hex, okay? Plus the displacement value, which is this thing. So 102 plus this thing, when you add it together, you're going to get 84. And that's somewhat intuitively obvious because 1 here lines up with the F here. And if you add F plus 1, you get a 0 with a carry, 0 with a carry, and all these things here turned into zeros, right? And then you're left with the 2 plus this 2, and you end up with 84. All right, so a little back of the envelope there, okay? So if you use program counter indirect with displacement, and your displacement is this value right here, and the program counter is 100, and the extension word within the instruction is 2 bytes into the instruction, this thing represents the address 84. The operand will be stored in memory at that address, which should be this value here, 2D13, and so on, right? Now, where's my scroll bar? I'm not in the right place here. 84 is 2D13BA27. Okay, so that's how that thing works. Now there's one more here. What do we got here? Program counter indirect with index. This is the exact same thing as this one here, but you add in an index register, okay? And I also did this notation because we'll expect to see 2 different versions of this, an 8-bit version for a small displacement and the exact same thing with a larger displacement value. Okay, now the reason that the 68K has two of them is to allow the programmer to use less memory to hold their program. This instruction is physically shorter because these extra bytes aren't stored in it. That's the whole ball game right there. And remember, these CPUs were made, 40 years ago, and memory was very expensive, so this was a big deal back in those days. So, again, it is the same as the previous one, but now we have the program counter for the base. We have the displacement. We have our index register. Again, we play the games with the scale value. What do we got going in my example here? We got program counter with a FFF82. I think it's the same thing we just had before. Yes, it is. We've got D1 for the index register and 4 for the scale. And we remember that D1 has the value 1 in it. Our scale is 4, therefore this value is 4. So we've got this value here. 102 plus the 802 gives us 84. Plus 4 is 88. And if we go look at the memory, we find out that's the value stored at 88 because we're doing an example of a read. Again, another read operations, okay? So if we go look at 88 really quick, and I'm really good at missing that scroll bar for some reason. 88 is right here, D6, or DC1651. DC1651, and so on, right? Okay. So that's how you work these examples. That's how you read these diagrams. Now, the rest of these are pretty simple. Program counter, memory, indirect, post-indexed. I spoke too soon. I said simple because my examples are very short. Now, the short of these are, look, these are the exact same ones as the pre-indexed and post-indexed indirect thingies that we just talked about up here, okay? That's these gigantic ones. The memory indirect, post-index, memory indirect. It's the same exact thing, except instead of using an address register, we use the value of the program counter plus 2, right? So I'm not going to go work an entire example and change nothing other than the base register. But you look closely at these diagrams in here, you'll see these look exactly like the other ones. Here's the base register, which this time is the program counter. And again, it's the address of the extension word within the instruction being executed. This is the one with the post index because it's after the indirection, okay? And the next one down here is exactly the same as the pre-index. We now see the index up here and the scale and so on. All right. The only difference is this was the address register before, and now it's the program counter, specifically the address of the extension word within the program instruction, which is usually 2 to 4 bytes into the instruction. And then we grab the indirect and apply the outer displacement there. Okay. So that's these two. I don't need to work a whole example. I'll leave that as a task for the viewer. Absolute addressing. The most wonderfully simple way to do this. Just put the address that you want in the freaking instruction. Okay? We have all this craziness. What happens here is you have an immediate value, an immediate operand inside the instruction within which you just put a hard-coded address right in there. And that address represents where the operand is. So if I have an immediate value stored in an instruction whose value is 88, then the memory address 88 will hold the operand that I want. And we just worked an example, and that's the value that was stored in 88, so that was right. The only thing simpler than absolute addressing is just immediate. In this mode, the immediate value itself is the operand. You put the operand right in the instruction. So if you want to put 88 into a register, you can say something along the lines of load register like D5 with 88, and it'll just put 88 in that register. So there's a walkthrough of a couple of somewhat wonky and advanced addressing modes. You don't normally see these anymore. This was all the rage in the 80s. They have CPUs that have really crazy instructions and stuff like that. Very complex, what we call complex instruction set. CISC. designs were all the rage in the 80s. Nowadays, it's RISC for reduced instruction sets. So you have less options, less addressing modes, fewer instructions, less complexity. All right. So why did we do this crazy stuff back in the day, right? Why did we have complex instruction sets? Well, it was thought that it was easier to program, and in many ways it is. These crazy addressing modes allow you to create things like hash tables and tables of pointers and things like that, complex data structures, where in one single machine instruction, you can follow pointers and go through linked lists and stuff like that really easily at the assembly language level. So this was a nice thing to have. And remember, like I said earlier, memory was very expensive. So if you could have an instruction do the same thing that 10 instructions could do today in a RISC machine, that's that much less memory that would be used to hold that program. In those days, machines were slow, everything was slower and much more expensive. So speed of the CPU itself doing these complex things was not that big of an impact. It was not so much a concern as it is today. Right? Having the instruction do many things actually resulted in faster running programs back then. Today it causes other problems, and the cost goes up, heat goes up, too many transistors, it doesn't scale well is the problem. So we've made a full U-turn and say less is more. Waste memory, not CPU operations. All right, so there you go. There's a walkthrough of a bunch of historically common addressing modes. I hope we all learned something, and maybe what we learned was an appreciation for RISC-V. Thanks for watching. See you next time. Bye.